So why do we need survival analysis? That's the first thing. Is that okay? Why do we need this survival analysis? We've done all these kinds of regression models. Can they fit into survival analysis? For you to be able to answer this, you need to understand what survival data is. Is that okay? Now, when we speak about survival analysis, there must be something we are calling an event that you are interested in. Is that okay? An event. So anytime you want to speak about survival analysis, you must be able to tell somebody what your event of interest is. And the event of interest can be different from one case to the other. Is that okay? So, for example, if your event of interest is, for example, death, then survival data will come from how much time from a starting point up to until that event of interest, which is death, occurs. Is that okay? If your event of interest is, let's say, divorce, then in survival analysis, we'd be analyzing the time duration from when a couple gets married until when they file for a divorce. Is that okay? If your event of interest is something we call recidivism, basically, recidivism is when somebody repeats an offense. Is that okay? A prisoner is taken in, serves, let's say, 2 years in prison, and is released back to the society. Then the day he or she is released back to the society, you can start counting from then. How long will it take before that person repeats an offense or does another offense? That study of reoffending is what we call recidivism. Is that okay? So in that case, the event of interest will be repeating the offense. Is that okay? Now, in survival analysis, the random variable of interest that we usually want to analyze is that time duration between a clear starting point until that event of interest occurs. Is that okay? Any question up to that point? Any question up to that point? So if you look at the screen, it is showing what is survival analysis. And for you to start discussing it, first, you must say that there's an event of interest. Is that okay? Then the dependent variable in that kind of analysis, or the variable of interest, the outcome interest, is usually duration or time until that event occurs. Is that okay? Can the dependent variable be negative? It cannot be negative because you are starting at a point and you are looking forward to time until that event occurs. So the random variable in that case is usually time, and usually denote that random variable by t. We don't use y, we don't use x. Is that okay? We usually denote it by t because it's measuring time until something happens. Is that okay? Now, if that event of interest occurs, then we say that failure has happened. Is that okay? If that event of interest occurs, then we say that failure has happened. I'm looking at in that first page, the page that I'm showing on the screen, the thing that we're saying event. Event is just equivalent to when the failure happens. Is that okay? Okay, and the examples there, I'm zooming in the examples. Maybe Parfait, you can read for us the examples 1 to number 6. But then what is remission? Remission. For those who are in the medicine world, anyone with an idea what remission is? then you might be interested in checking how long does it take until the cancer comes back. It might come back, it might fail to come back. Is that okay? So you can check duration between the time the treatment was done and how long it took before the cancer reappeared, if it appears. If it doesn't appear, we'll discuss what that means. Is that okay? Then the next one, number 2. So time until somebody develops a heart disease. Uh-huh. Mm-hmm. So once somebody hits 60, you start checking how long after hitting 60 will this person take before the person dies. Is that okay?
Yes.
Uh-huh.
And the next one is parolees, recidivism study.
Parolees are people who have been, I think, have been released from prison.
Okay.
They are
Time
parolees.
until
Uh-huh.
yeah, time until release in weeks.
Rearrest in weeks. So once somebody is released from prison, the person, most likely the person will offend again. So how long does it take for this person to stay without making a mistake that makes him or her to be arrested? Is that okay?
Yes.
Then number 5.
Number 5 is heart transplants, time until death in months.
Time until death. One thing that you should be able to see in this unit is that the random variable or the outcome variable of interest is time until an event. Is that okay?
Yes.
And the time can be measured in different units. It can be in months, it can be in weeks, it can be in years, it can be in seconds, it can be in minutes, it can be in any form. So time can be in any units. Is that okay?
Yes.
Okay. Guys, but somebody can ask, why don't we just analyze? If this is just a random variable time, why don't we just analyze that one and finish? Now, the trick comes in, and what makes survival analysis special that makes you to just do survival analysis and nothing else is what we call censoring. Is that okay? Is that a question? So what makes survival data special is this issue of censoring. Is that okay?
Yes.
What is censoring? Now, think of this. Let me just get my pen and I try right on the screen. Think of this. So this is the starting point. Is that okay?
Yes.
And you must follow people over time because you are recording how long it takes before something happens. Is that okay?
Yes.
If it's a cohort, then you need to follow them over time. Sorry, can you hear me now?
Yeah, we can hear you now.
Hello?
Yes.
Sorry, a call came in, and most likely the person will make the call again. So in terms of survival analysis, we can record how long it will take before that person makes that call again. So the event of interest will be that person making another call. Is that okay?
Yes.
So survival data can come from anywhere. Now, so we have a starting point, then we are following. Is that okay? So we are following them over time, assuming that we say that we'll follow them for the next 20 years. Is that okay?
Yes.
Then, so this is the period of 20 years. So we are still at the starting point, and we've declared that we'll follow them for 20 years. Is that okay?
Yes.
So let's say this one is, let's say, after 5 years, and this one is after 10 years, and this one is after 15 years, and this one is after 20 years. Is that okay?
Yes.
So we follow, this could be the first couple, second couple, third couple, fourth couple, we follow them. Is that okay?
Yes.
For example, the first couple here, let me call this couple number 1, this couple number 2. Couple number 1, we follow that couple until around, this is what, around 7 years. Is that okay?
Yes.
After 7 years, they break up, they divorce. Is that okay?
Yes.
So the event of interest was divorce, and it has happened, we record 7 years. Is that okay?
Yes.
This other couple, we follow them, then the event of interest, they divorced after 10 years. Is that okay?
Yes.
This couple here, number 3, we follow them, they divorce after 15 years. Is that okay?
Yes.
There's couple number 4 here that we've been following, and by the time we are closing the experiment, this couple have not divorced. Is that okay?
Yes.
What do you record? Did they take to divorce? I'm not asking to affair alone. I repeat again.
Yes.
This couple number 4, we follow them over time, and by the time we are closing our experiment after 20 years, they've not divorced. What will we record for them as their time for divorce?
It should be 0.
Oh, 0 means they divorced immediately, they got married. I thought you would know. Remember, we are recording the duration until the divorce happens. Perfect.
Yes.
If we record 0, t is equal to 0, what does it mean?
Understand now.
You understand? It means they divorced immediately. They just got married today, and when they just go back to their home, they didn't make any business. They just close the business on that same day.
Yeah. Yes.
So what will we record for this person? Oganga, are you there?
Can we be able to have something like null event?
We need to record something for that person. What do we record? Oganga was trying to respond. Oganga?
Recording in progress.
Oganga, are you there? I'm trying to look for other people, but I can't access. Okay, I can access. Consolata?
Hello. I'm not sure, but infinity, I don't know. Sorry.
Infinity, does it mean that they went to infinity years?
No, but they surpassed the time period that we are looking at.
Almost there. Peter Wabuya, are you there? So we have Peter Wabuya, then Olo Brian. Peter? So, okay, let me proceed. Olo? Any attempt?
Can we say 20, given that the time period was 20, but unfortunately the outcome didn't occur during that time?
That's William, right?
Yes.
Partly correct. So this is what we'll do. So that is an example of censored data. Is that okay?
Yes.
Let me try writing on the screen. So we'll record T will be equal to, sorry, need to get the writer. So we'll record T is equal to 20 for that person. But if we put T is equal to 20, then it means that they divorced after 20 years. Is that okay?
Yes.
Which is not the correct position. We know that by the end of 20 years, they are not divorced. Is that okay?
Yes.
So it means that the divorce happened somewhere after T is equal to 20, somewhere after 20 years. Is that okay?
Yes.
If it happened, is that okay? So
yes.
we usually put a plus. So we say T is equal to 20 plus to show that it occurred somewhere after 20 years. And that is an example of censoring. Censoring is when we do not observe full information until the event of interest occurs. Is that okay?
Yes.
And there are two types of censoring. So anytime you see a value together with a plus, it shows that censoring happened there. Is that okay?
Yes.
Now, there are two types of censoring. There's left censoring and right censoring. Is that okay?
Yes.
For example, assuming that we've identified 30 couples, is that okay?
Yes.
But we know that they wedded within the last 5 years. Is that okay?
Yes.
And we want to study and see how long it takes before they get a divorce. Is that okay?
Yes.
Assuming that there is information that, oh, these guys, there's one couple that has been in court, and actually, by the time we are starting our study, months before, the divorce went through. So we are starting our study, we had identified these people as people that we want to follow, because we know they got married around 5 years ago, but they got married after 1 year, they started, wrangles, and they decided to go for divorce. So by the time we are putting them in the study, the event divorce had already occurred for this couple. Is that okay?
Yes.
Then that one will be left censored, because the censoring occurs before the study starts. Is that okay?
Yes.
Then now, right censoring is the censoring that occurs after the study has started. Is that okay?
Yes.
And one example is where the time period of the study ends and the event of interest has not occurred, then the data for that individual or item will be censored. Is that okay?
Yes.
Another case is where you start the experiment. Is that okay?
Yes.
And remember, you are following them over time. So anytime you hear following people over time, what must come into your hand is into your mind is a cohort study. A cohort study where you follow people over time, going forward into time. Is that okay?
Yes.
Now, for cohort study, including longitudinal study is also part of the cohort study. Is that okay?
Yes.
Where you follow the same person over time. We'll give you a longitudinal study and it's part of a cohort study. Is that okay? One problem with the longitudinal study or cohort study is loss to follow up. Loss to follow up. Where you've been following this person for 2 years, then the person disappears or changes location and you cannot track the person. Is that okay?
Yes.
For example, the couple was staying here, then you follow them first year, you checked, there was no divorce. The second year, there was no divorce. The third year, you go back again to that house, you hear that those people relocated to the US and nobody has their contact. Is that okay?
Yes.
So you followed them for 3 years, then after 3 years, they relocated to US and nobody has their contact to know anything. Would you say that they've divorced?
No.
You don't know. Is that okay? What you know is that they stayed together for 3 years. So you'll say their T will be equal to 3 years, but with a plus to show that we don't know when the event might have occurred. Is that okay?
Yes.
So because this is happening, the censoring, so this will be censored data, but it's happening on the right-hand side after the study had started. So we call it right censoring. Is that okay?
Yes.
Okay. Let me get out of this. So, okay. Okay, so that's censoring. Any question on censoring? And somebody read for us this section here. There are generally 3 reasons why censoring may occur. Any person who feels inspired to read. Any person. Rafael, maybe you can read for us if nobody is inspired.
I can read.
Okay, please do.
Okay, so there are generally 3 reasons why censoring may occur. 1, A person does not experience the event before the study ends. 2, a person is lost to follow up during the study period. And 3, a person withdraw from the study because of death, if the death is not the event of interest, or some other reasons, for example, adverse drug reaction or other competing risk.
Competing risks.
Yeah.
Notice that, what is the difference between number 2 and number 3? William, right again.
So I can say for number 2, this person just disappear without a trace.
We don't know where that person is.
Yes.
Is that okay?
Yes.
Yeah.
And then number 3, the person withdraw willingly. So meaning, like, you might know the person where he is, but he's not willing to continue with the study. Yeah.
Exactly. Is that okay? Is that okay?
Yes.
Okay. Now, just a quick one. I'll need you to read later on this example of these five people: person A, person B, person C, person D, and person E, and person F. Is that okay?
Yes.
Later on, notice they are not starting at the same time point. Can you see person C is starting somewhere at week 4? Person C. Is that okay?
Yes.
So in survival analysis, we are usually not interested with them starting at the same starting point. We usually say that they have staggered entry into the study. They can have staggered entry. They can start at the same starting point, or they can have staggered entry. Is that okay?
Yes.
But the focus is the duration of time, not when you started. Our interest is the duration of time. Is that okay?
Yes.
Okay, so let me proceed down. Okay, I want to come and cover this survival function. There are 3 functions that are usually of interest that we'll be discussing. Is that okay?
Yes.
The first one is called the survivor function, which is denoted by ST. Is that okay?
Yes.
The second one is the hazard function HT. The third one is the PDF of failure time, which is FT.
Yes.
And the last one is cumulative hazard, which is the HT, capital HT. So there are 2 H's. There's lowercase HT, so there is lowercase h and capital H. Lowercase h, we call it hazard function. Capital H, we call it cumulative hazard function. Is that okay?
Yes.
So I want to discuss this, but it will be important if I write on the screen. Is that okay?
Yes.
So let me stop sharing this, then I write on the screen. Just 1 second. Are you able to see the whiteboard?
Yes.
Okay, just 1 second. Okay, good there. Now, remember, the event of interest is time till the event, capital T. We denote the random variable, capital T. Is that okay?
Yes.
Now, if somebody survives up to time T, is that okay?
Yes.
Then the person has survived. Survival is the function up to time small t. Is that okay?
Yes.
Then the survival up to time t is actually equivalent to the probability that that person, the time recorded for that person is greater than time t. Remember, t is recorded is the random variable that stores how much time somebody survives. Is that okay?
Yes.
For you to be said to have survived up to time, a particular observed time t, which you are denoting as ST, is the probability that the random variable t for that particular person is at least the small t value. Is it making sense?
Yeah.
For you to be able to be said to have survived up to time t, then it means that the probability, it's a probability of having your capital T, the random variable t for you, being greater than that value that we're observing the small t. Is that okay?
Yes.
So this is the definition of the survival function, S of t. It's the probability that a person survives up to time t, or dies after time t. Surviving up to time t is equivalent to dying after time t. You don't die before t. Is that okay?
Yes.
Notice I'm talking about this t, the lowercase t. T is the random variable. So you've lived up to time t. Is that okay?
Yes.
Guys, any question about this? This is the key point, is the underpinning for survival analysis. So the survival function is just a probability. If you survive up to time t, then it means that your capital T must be greater than that small t, the observed capital T. Is that okay?
Yes.
So this one denotes the probability of being alive at time t. The probability of being alive at time t is what we call the survival function. Is that okay?
Yes.
Now, if our t is equal, what is S of 0? By the time you are starting, what is the probability that you survive up to time t? 0. T is equal to 0. Hello?
Yes.
Think of this. I've taken 15 couples. Is that okay?
Yes.
And assuming that we are all starting at the same time at t is equal to 0. Is that okay?
Yes.
We are starting with 15 couples. Is that okay?
Yes.
What is the probability of the 15 couples? What is the probability of couples surviving time t is equal to 0? Up to time t is equal to 0.
Could it be 1, Professor?
It will be 1, because at that point, everybody is alive. Is that okay?
Yes.
So, and what is the probability that the couple will survive to infinity, time infinity? Remember, infinity is a very, very large number, positive number.
0.
It is 0. Is that okay?
Yes.
Things will have to happen at some point somewhere ahead there. Is that okay? And if you think of our event being death, then death will occur at some point. Is that okay?
Yes.
So then it means that the survival function from time t is equal to 0 to t is equal to infinity, assuming that this is the ST, is that okay?
Yes.
What is the largest value that you can have for S of t, survival?
It's 1.
It's 1 when you are all surviving at the beginning. Is that okay?
Yes.
Then after that, remember at infinity it will be 0. Is that okay?
Yes.
It cannot go upwards. The survival function is a reducing function, so it will go down. I'm just giving an example. It might not go down in that shape. Is that okay?
Yes.
So always the survival function will be going down in that shape. Is that okay?
Yes.
So automatically the survival function is a decreasing function. It's a decreasing function. Is that okay?
Yes.
And the largest value that you can have is a 1, and the smallest value you can have is a 0, because it's a probability by itself. So in terms of properties of the survival function ST, the highest value is 1, the lowest value you can ever get is 0. It is always a decreasing function going downwards. Is that okay?
Yes.
Is that okay?
Yes.
Now, guys, I'm just going to do the opposite of this. Is that okay?
Yeah.
So the opposite of that will be probability of t less than or equal to t. Is that okay?
Yes.
Do you know this function? Have you ever seen it anywhere? Come again? In most of the time, you usually meet it in this form. Probability that x is less than or equal to x. You usually meet it in that form. Do you know this function?
Yeah.
What is it called? Remember, it is the probability from the smallest value that you can get up to, so it's like integrating something from negative infinity up to x. It is from the lowest value that you can get up to x, or x going downwards. You've not met such a thing? Have you met such a thing? It's
I think I
called,
have encountered it. Yeah.
it's the CDF, cumulative distribution function.
Yeah.
We usually denote it by capital F of t. Is that okay?
Yes.
The capital F. So we usually have small f of t. What is small f of t? Is a PDF, probability density function. Is that okay?
Yes.
Then capital F of t is the CDF, cumulative density function, or cumulative distribution function, not density. Is that okay?
Yes.
How do we get f of t, capital F of t? We get it by integrating the small f of t from negative infinity to up to the t value itself. If you integrate the small f of t, you get the capital F of t. Is that okay?
Yes.
Then automatically, if you differentiate the capital F, you get the small f. Remember, differentiation and integration are opposite of one another. Is that okay?
Yes.
Now look at this. Let me see. Let me go to a new screen, new whiteboard. Let me save this one. Save. Now, remember S of t. Sorry. Remember, S of t is equal to probability of t being greater than t. Is that okay?
Yes.
Now, let me draw a number line. If this is your t, is that okay? So f of f, sorry, this is negative infinity, this is positive infinity. Is that okay?
Yes.
Remember, the probability of the entire stretch, total probability is usually equal to 1, right?
Yes.
Total probability is usually 1. Is that okay?
Yes.
But from t, sorry, for t greater than capital small t, this part here is the S of t. Is that okay?
Yes.
And what is this part? From negative infinity to t, what is that one?
The PDF.
Is there?
PDF.
Negative infinity to t. Let me take it back. Negative infinity to t.
F of t.
There are two f of t's. There's small f and there's capital F. So we have to be clear at this point. The
Capital
small f. Negative infinity to t is the CDF. People have typed in the chat box. So it is the CDF. Is that okay?
Yes.
So this is the CDF, f of t. Is that okay?
Yes.
But the total combining from there up to the entire stretch is 1. That is the total. Is that okay?
Yes.
Remember, the total probability is usually 1. Is that okay?
Yes.
So if this is S of t, are you able to see that there's a relationship between S of t and f of t?
Yeah.
Remember, f of t is equal to probability of capital T being less than or equal to lowercase t.
Mm.
Is that okay?
Yes.
So this part is actually 1 minus this part, 1 minus the other one. Is that okay?
Yes.
Is that okay?
Yes.
So guys, what I wanted you to see is that actually the S of t is just equal to 1 minus f of t, or the vice versa. Similarly, f of t is equal to 1 minus s of t. Are you able to see that?
Yes.
One way to look at it is to look at the number line, and t is at this point. From this point going, from t going to infinity, basically, that one is your s of t, because rather than small t, it means anything to the positive of t. So it is t to infinity, that is your s of t. Then the remaining part, which is negative infinity to t, basically that is the CDF, which is the capital F of t. Is that okay?
Yes.
So there's a relationship between capital F of t and S of t, and the relationship is that F of t is equal to 1 minus S of t. Is that okay?
Yeah.
And remember, f of t, you can get the small f of t by differentiating f of t, capital F of t. If you differentiate the CDF, you get the PDF. This is from probability and statistics. If you differentiate the big F, you get the small f. Is that okay?
Yes.
If you integrate the small f, you get the big F. Remember, integration and differentiation are usually one is the opposite of the other, basically. Is that okay?
Yes.
Is that okay?
Yes.
Okay. Now, we've also seen that if you differentiate, we know that capital F of t is related to S of t. With that one, we know. We know that small f of t is related to capital F of t. Then automatically, f of t is related to S of t. Is that okay?
Yes.
I'll come back with the relationship. So I've introduced two functions. We have the S of t. We have the small f of, with the small f of t. Is that okay?
Yes.
I want to introduce another function called the hazard function, which is the h of t. Is that okay?
Yes.
The hazard function is not a probability. Let me save this. Save. The hazard function h of t, h of t is what we call the hazard function. Is that okay?
Yes.
It is the instantaneous risk. If the event was death, let me just use death because it's easy to understand. Ideally, I'm supposed to say instantaneous risk of the event. Is that okay?
Yes.
At time t. Is that okay?
Yes.
So this means that you've survived up to time t, then now the hazard now will be the probability that you actually die at that time t. That's what we mean by instantaneous risk of death at time t, the hazard function. Is that okay?
Yes.
So you've survived up to time t, and we are saying that now the hazard is now what is the probability that you'll die? Or what is the chance that you'll die? It's not directly a probability. What is now the risk of you dying immediately after just arriving at that time t? After surviving up to time t, then what is die instantaneously? Is that okay?
Yes.
Just 1 second. Our guy has called, so let me just respond and say I'll call. Otherwise, he'll not stop calling. Is that okay?
Yes.
Now, what is this h of t? Now, let us think of this. You survived up to time t. Is that okay?
Yes.
Then we say we give you a very short time span, which we call delta t, or change in t, a small change in t. The change in t can be even a fraction of a second. Is that okay?
Yes.
So think of that. So it means what will be this time point here? What will be that time point?
Zero.
Yeah.
It will be t plus in t.
It will be t plus the small change in t. Is that clear?
Yes.
Now, we are looking at, so the hazard is the probability, is the risk of you dying within this small window here, within that small window. Because you've survived up to time t, but we're just giving you an additional small change in t. And we are looking at the probability that you'll die within that small window of change in t. Is that okay?
Yes.
So in short, the hazard for h of t will be equal to the probability of your time of event, the event occurring is greater than t, but less than t plus the change in t. Is that okay?
Yes.
Given that you had survived, let me just write it again. So h of t will be equal to, there's something I'll write here, but for now, let me just ignore it. T less than capital T less than t plus change in t, given that you are survived up to time t. That is the hazard. Is that okay?
Yes.
Then we make sure that we introduce limits. We introduce limits and we say that the limit that this change in t actually approaches zero. So we are making that window to be very small. We are making this window to be very small so that it is the instantaneous death. After just arriving at time t, immediately, a few microseconds later on, you die. Is that okay?
Yes.
So h of t, you must survive up to time t. Then you are saying that almost immediately you survive up to that time. Few microseconds later, you die. That is the hazard. Is that okay?
Yes.
And from this is conditional probability. There's some gymnastics you can do here. This is conditional probability, right?
Yes.
If you look at it, remember, conditional probability comes from Bayes' theorem. You guys did Bayes' theorem, right?
Yes.
And the Bayes' theorem states that probability of A given B will be equal to what? Probability of A given B will be equal to what?
I think it's probability of B given A.
It is A intersection B
Yes.
of probability of B. We use the conditional probability. It's also called the Bayes' theorem.
Yeah.
Is that okay?
Yes.
A intersection B over probability of B. You can write it in terms of the conditionals, but I want you to see it in terms of the intersection. Is that okay?
Yes.
We can actually rewrite it the way William was showing. We can derive and show from this what he wanted to say. I'm sure he wanted to say probability of A given B, sort of B given A times probability of A divided by probability of B, something like that.
Yeah.
Is that okay?
Yes.
Now, same thing here. We are looking for this conditional probability. Is that okay? I'm leaving the limit outside for now, for simplicity. Is that okay?
Yes.
So this will be equal to probability of what? It is given this. So this entire thing is our A, and this other thing is our B. Is that okay?
Yes.
So A given B, so what do we need to get first? We need to get the intersection of the two. Is that okay?
Yes.
So it will be probability of T greater than T less than T plus change in T intersection T greater than T, right?
Yes.
Divide by probability of what? Hello?
T greater than T.
T greater than T.
T greater than T. Is that okay?
Yes.
So this is our H of T. Notice that I've just left the limit only in between here. We don't need to worry about it. We just know that we make change in T very small. Is that okay?
Yes.
But now, T less than T, remember this one has an equal sign here. Sorry. T less than T, sorry, the capital T is greater than small t, but is less than T plus change in T. Is that okay?
Yes.
We want the intersection between a capital T, which is greater than T, less than T plus change in T, and the intersection of T greater than or equal to T. What is that intersection? As the change in T becomes very small. Okay, let me leave that one first. Let us start with the denominator. What is this denominator? What is the probability of capital T? What is the probability of capital T greater than T? Probability that the person's survival time, capital T, is greater than T. Basically, that is the definition of survival. You remember survival?
Yes,
The S of T, correct, Abigail? It is the S of T. So the denominator is basically the S of T. Is that okay? From our starting point, we say that probability of capital T greater than T is basically the definition of S of T. Is that okay?
Yes.
Now we're okay with that. Let us go to the numerator. The numerator is, let me get a new whiteboard. It is, the numerator is t greater than t less than t plus change in t intersection t greater than or equal to t. Is that okay?
Yes.
What is the intersection of these two? When they change, remember there's the change of t. The change of t is always approaching zero. It's becoming smaller and smaller and smaller and smaller. It's a limit. What is this intersection? Let me draw it in a number line. Is that okay?
Yes.
So this is the number line. This is t. Is that okay?
No.
And we've added a change of t. Is that okay?
Yes.
And it's bringing us to t plus change in t. Is that okay?
Yes.
But we are making this change in t to become smaller and smaller and smaller and smaller. Is that okay?
Yes.
Now we want this intersection where it is intersects with t greater than or equal to t. What is the intersection?
I think it will be t.
It will be exactly t.
Yeah.
Remember, t plus change in t, and you're making the t to be small, but you want the intersection of that width between t and change in t, this width. You are making it smaller, but you want it to be intersected with t greater than t. Remember, t greater than t is this entire length. So where do these lines meet? These two lines. There's this line, which is the t greater than t, right?
Yes.
And there's this other line from t going to t plus change in t. Is that okay?
Yes.
But you are reducing this change in t to be very small. What is the intersection of these two lines? At what point do the two lines overlap?
At point t.
Why not in between t plus change in t?
Because change in t is almost going to zero. So
the change of t is going to zero. When it's going to zero, then where is it going to? Where is this duration? This span. Where is this span going to? This span. As change in t becomes zero, where does it head to? Does it become longer or shorter?
shorter.
It becomes shorter when it's the smallest, almost at zero. Where is it at? It's at t, right?
Yes.
So the intersection between these two lines actually will be at the point t. So it means that the numerator, so we'll have h of t will be equal to probability of t is equal to t over probability of t greater than t. Is that okay?
Yes.
But h of t, we've already seen that the denominator is actually s of t. Is that okay?
Yes.
But probability of t equal to t, which is just, I know you're used to this, probability of x is equal to x. What is this equal to? It's usually equal to f of x, lowercase f of x, the PDF.
Yes.
So it means, what is this numerator? What is this numerator? It is the PDF, which is the lowercase f of t. Is that okay?
Yes.
So given h of t, we are getting a relationship here. The hazard function is equal to the PDF divided by the survivor function. Is that okay?
Yes.
So if we give you the hazard function and we give you the survival function, how do you get the f of t? If we give you the hazard function and we give you the survival function, can you get the f of t?
Yes. So you multiply. So
You multiply.
Yeah, with
Correct.
the
Correct.
s of t.
Correct. Is that okay?
Yes.
So
Yes.
We just want to do a few things. 15 minutes, we should be done in 15 minutes. Now, so it means that once we know the S of t and we know F of t, then we know H of t. Is that okay?
Yes.
So most of the time in survival analysis, we are usually interested in the S of t. We are interested in the H of t, the hazard. Is that okay?
Yes.
So in most of the cases, we'll be told to estimate H of t or S of t. We are rarely told to estimate F of t. Is that okay?
Yes.
Okay, now. So S of t is the survival function. Is that okay?
Yes.
New whiteboard. So estimating S of t, the survival function. Is that okay?
Yes.
Guys, there are several ways of estimating this S of t. Is that okay?
Yes.
There are three ways actually. The first broad way is parametric approach. Is that okay?
Yes.
The second one is called semi-parametric. And the third approach is called non-parametric. Is that okay?
Yes.
Non-parametric means that you do not assume any distribution for the survival data. So you are just given the survival data and you estimate the survival function. Is that okay?
Yes.
Parametric, which is on the far end, it means you are assuming a distribution for the survival function. Semi-parametric, it means halfway you are assuming distribution, halfway you do not assume distribution. Is that okay?
Yes.
If you do not assume distribution, that is the non-parametric, it means you are just using the data only and you estimate the survival function. Is that okay?
Yes.
Now, guys, our interest is to estimate the survival function. We've said that there are three approaches: parametric, semi-parametric, and non-parametric. Is that okay?
Yes.
The non-parametric way, the actual name is usually called Kaplan-Meier. Kaplan-Meier Meyer estimator of ST, of the survival function. It is the non-parametric way. Is that okay?
Yes.
The semi-parametric way, the ultimate semi-parametric model is called the Fox proportional hazard model, Fox pH model. Is that okay?
Yes.
Parametric way, it depends on the distribution that we choose. Is that okay?
Yes.
I want us to start with the non-parametric way, which is also called the Kaplan-Meier estimator. Is that okay? It's a non-parametric. Yes. All these are approaches for estimating the survival function. Is that okay?
Yes.
Another name for Kaplan-Meier estimator is the product limit estimator. Product limit. In short, we'll be multiplying some. Product means multiplication. We'll be multiplying some things. Is that okay?
Yes.
Now, let us start simple. We want to do Kaplan-Meier, then we stop there. So, I mean, we'll try and stop at the top of the hour, but it will be good if we finish this and we run a quick R code with an example. Is that okay?
Yes.
Now, think of a data set. Assuming that you want to estimate people who have survived up to time 1, those who have survived up to time 2, those who have survived up to time 3. Is that okay?
Yes.
How do you get those who have survived at time 1? Ideally, you'll count how many people are alive. Is that okay?
Yes.
At that time, point 1, divide by the number of people who started. Is that okay?
Yes.
It will give you survival. How many people are alive? Divide by the number of people who have started. Is that okay?
Yes.
What about at time 2? At time 1? at time 2. How do you get the survival at time 2? Again, you'll just count how many are alive at time 2, divide by the number who are alive, sorry, who are at risk at that start of time 2. At risk of dying at start of time 2. Is that okay?
Yes.
Similarly, if you want at time 3, probability of surviving at that time 3, it means that you've arrived in time 3, but you survived that time 3 period. Is that okay?
Yes.
Make sure you understand this, guys. This is where the trick is. This is 0, this is time point 1, time point 2, time point 3. Is that okay?
Yes.
Surviving time 1, it means that you are alive up to this time point 1 before you go to this time point 2. Is that okay?
Yes.
Now, at time 3, survival at time 3, it means that those who are alive, number alive at 3, divide by risk at 3. Is that okay?
Yes.
Now, if you assume that there is independence of you dying before and you dying at that time 3, at time 3, at time 2, at time 3, then if you recall, if two events are independent and B, the probability of A and B will be equal to the product of the two. Is that okay?
Yes.
So for you to survive at time 2, then it means you must have survived time 1, you've survived time 2. For you to have survived time 3, then it means that you have survived time 1, and you have survived time 2, and you have survived time 3. So to get survival into a time point ahead, then it means you have to multiply the probabilities of survival at all those different time points until you reach that time point of interest. Is that okay?
Yes.
Now, guys, for simplicity, S of t will be estimated by, at any time, the probability that you are alive, assuming that at time j, let us say at time j, Rj people are at risk of dying. Is that okay?
Yes.
Let me use Nj. Let me use Nj so that it's in line with the book that you'll be reading. Assuming that at time J, Nj people are at risk of dying. Is that okay?
Yes.
And during time J, do subscript J people die. Is that okay?
Yes.
What is the probability of dying within that time J? So this is the period J. Is that okay?
Yes.
Those who enter that period, those who come into that period at the starting point here, Nj of them arrived there alive. Is that okay?
Yes.
During that period, DJ people died. Is that okay?
Yes.
What is the probability of dying within that time period? Dying will be correct, Abigail. It will be DJ, those who die, over the number of people who are at risk. Is that okay?
Yes.
Then what will be the probability of surviving that period? This is the probability of dying within that period. What is the probability of surviving within that period?
Is I think NJ minus DJ.
What is NJ?
Yes.
Will it
What is
be 1
NJ?
minus
Huh?
1
One
minus
minus.
DJ over NJ?
it will be 1 minus dj over nj. Is that okay? So this is the probability of surviving that time point. Is that okay?
Yes.
So at any duration, any window you take, the probability will just be this one for each and within that window, but the numbers will be changing. Those who die within that window, those who are alive within that window, at the beginning of that window. Is that okay?
Yes.
So it means to get the survival, then we'll be multiplying these probabilities as we go on. For j less than t, we'll be multiplying 1 minus dj over nj. For all the period going down. So you take each period, you calculate, each period, you calculate, each period, you calculate. Then to get survival up to a certain time point, you multiply all the time periods up to that time point. Is that okay?
Yes.
Is that okay?
Yes.
So this is the Kaplan-Meier estimator, the KM estimator of the survival function. Notice that it only uses the observed times. How many people died? How many people are alive? No parameters. There is no beta, there is no alpha, there is nothing, just the numbers. Anytime you see a model which uses the data without any other thing, any parameters, then that is a non-parametric method. Is that okay?
Yes.
Quick example, a small example. Consider the data below. Uh, 1, 5 plus, 6, 6, 8, 8 plus, 9, 11 plus. Is that okay?
Yes.
Assuming that this is death. So it means that this person number 1, notice these are T. These are the survival times. Is that okay?
Yes.
So these are the T. So person number 1 experienced the event, died at time point 1, one day or 1 year or something. I'm not interested in the unit at this point. Is that okay?
Yes.
Person number 2 survived up to time 5. Is that okay?
Yes.
But was censored. That's why we have a 5 plus. So we know that the person survived up to time 5, but after time 5, we don't know. Is that okay?
Yes.
So this is person 1. This is person 2. Remember, the values are time. This is person 3. What happened to person number 3? Did they experience the event of interest? Did they experience the event of interest? Notice that if they don't experience the event of interest, then it means that they were censored. The censoring will always denote with a plus. Is that okay?
Yes.
So person number 1, did he or she experience the event of interest? Person number 1, did he or she experience the event of interest?
Yes.
No. Huh? Okay.
Yes. Let me repeat again. Is that okay? If it has a plus, then it means that person was censored. The person was observed up to that time point, but either we lost that person to follow, the person withdrew. Is that okay?
Yes.
So we are recording it with a plus to show that we did not see the event of interest. We did not see the death because the person disappeared. Is that okay?
Yeah.
But it happened somewhere past 5 years. That's why we are still saying 5 plus. Is that okay?
Yes.
Okay. Person number 2, did the person experience the event of interest?
No, he didn't.
The person did not experience. That's why we see a censoring. Is that okay?
Yes.
Person number 3. Now, person number 3, did the person experience the event of interest?
Yes, he did.
Yes, he did. At what time?
At 6.
At time 6. We don't care whether it's 6 weeks or 6 years or 6 months. It's not of interest now. So time can be anything. Is that okay?
Yes.
Person number 4, did he or she experience the event of interest?
Yes.
And at what time did he or she experience it?
At 6 time
After
period.
6 time periods. Person number 5, did the person experience it?
Yes.
Yes, at what time point?
8 time
Person
period.
number 6?
No.
The person did not experience it. That's why we have an 8 plus. But we know the person survived up to time 8. Is that okay?
Yes.
Person number 9?
He did experience.
He did experience. Person number 11?
No.
Disappeared after time 11. Is that okay?
Yes.
Okay. Now, to calculate the survival function using the Kaplan-Meier estimator, then we need to arrange the time points. Is that okay?
Yes.
Our focus when making the table for Kaplan-Meier should be only on the the failure times. You only need to put the failure times. Is that okay?
Yes.
So, and you need to put them in order of time. Is that okay?
Yes.
What is the lowest failure time? What is the lowest failure time? Observed failure time?
It's 1.
It's 1. What is the subsequent observed failure time? It's 5 plus observed failure time censored. Some guys, John, I thought it was clear to you censoring and observed.
Yeah, I got that.
So the next failure time is which time point?
6.
Is 6. Is that okay? We do not need to repeat the 6. We do not need to repeat the same failure time. We just order them. Is that okay?
Yes.
The next failure time?
8.
8. The next failure time?
9.
9. Is that okay?
Yes.
Now, the next thing we need to record is how many people were at risk. Let me put this one instead. How many people were at risk at that time point? Is that okay?
Yes.
Let me put at risk. We are using N. NJ. How many people at risk at? I'm putting J to represent these different time points. Is that okay?
Yes.
And during that time point, how many people died? Is that okay?
Yes.
Then how many people survived? 1 minus DJ over NJ. Is that okay?
Yes.
So at time point 1, we're just arriving at time point 1. Remember, this is time point 1. We are talking of just arriving at this time point. How many people were available? So in our study, how many people do you have in total?
8.
You have how many people?
8.
8 people. Is that okay? Because this is person number 7 and this is person number 8. Is that okay?
Yes.
So just at the beginning of our study, when you're arriving at time point 1, at the beginning of time point 1, how many people were available? Remember, it's before something happens at time point 1. Is that okay?
Yes.
So just at the beginning, at the tip of the beginning of time point 1, how many people were in the study? How many people were in the study? 8 people were in the study. Is that okay? During that time, during the duration of time point 1, the entire period of time point 1, how many people died or experienced the event?
1.
1 person experienced the event. Is that okay?
Yes.
So what is the probability of surviving time point 1? So it is basically the number who survive. Sorry, 1 minus the number of people who died divided by the number of people who were at risk. Is that okay?
Yes.
So it will be 1 minus D over DJ D over N. Is that okay?
Yes.
So it will be 1 over what? Is that okay?
Yes.
Which is equal to what? The fraction, in terms of fraction.
7 over 8.
7 over 8. Is that okay?
Yes.
Let us go to the next time point, which is time point number 6. Is that okay?
Yes.
When you were just starting time point number 6, how many people were in the study? When you were just arriving at time point number 6, how many people were in the study?
7.
7?
6.
6?
6.
Somebody said 7, somebody said 6. Why 7? We start with the 7 person.
It's 6. It's 6. I've changed. It's 6.
6,
we
you are
lost
changing.
one
So
person.
why 6? Why 6?
Because one had died and that we lost one to follow up.
One had died, then one had died at time point 1, then at time point 5, we lost one to follow up. Is that okay?
Yes.
So those ones are 2 that we've lost, so it means we are left with 6 by the time we are arriving at time point 6. Is that okay? Is that okay?
Yes.
Then how many people experience death at time point? Please do not confuse this 6 and this 6. Is that okay? The 2 6 are different. So how many people experience death at time point 6? Within that time point 6, how many people experience death?
2.
2 people experience death. Is that okay?
Good. Yes.
So what is the probability of surviving there in terms of fraction after calculating? The answer here. I need a fraction. Guys, time is not good. You need to move fast. I need a fraction, a full fraction.
I think it's 4 over 6.
The correct answer is 4 over 6.
Yeah, 4 over 6.
4 over 6. Is that okay?
Yes.
So it is basically 1 minus 2 over 6. 1 minus 2 over 6, right? Which is 4 over 6. I don't want to reduce it so that you're able to see the values, the numbers from the original values. Is that okay?
Yes.
And now we go to time point 8. Is that okay?
Yes.
When we are arriving at time point 8, how many people are still alive? Or how many people are at
4.
risk? The NJ.
4 of them.
There are 4 of them. Is that okay?
Yeah.
How many people experience the event during that time point 8?
Oh.
Huh?
Only one.
You said 2 first, then now you changed to 1.
It's 1.
Why 1? Why not 2? Because we have 8 and 8 plus. Why not 1?
1 died at time point 8, and we lost one to follow up.
Remember, we just want to follow 8 plus. 8 plus, it means it's slightly after 8, not during 8. Is that okay?
Yes.
Remember, we were saying we cannot include the 8 plus inside the 8 because the 8 plus, the event was not experienced at 8. It means the event is being experienced somewhere after 8. We know it's past 8. Is that okay? So in real sense, only one person experienced it there. Is that okay?
Yes.
So what is the probability of survival for that time point? It is 3 over 4. Is that okay? And the next 9 point is at time point 9. How many people were at risk at time point 9?
2.
2 were at risk. How many people died at time point 9?
1.
But then why are we saying 2 people are at risk at time point 9?
It's only 2 people that made it to that time point 9.
Why not 3? Yet we have, because we had 4 at risk at time point 8, then we lost 1. Sorry, 1 died. Notice here, we had 4 at risk, 1 died. Why don't we take 4 minus 1 to give us 3?
The other one we can't really tell what happened to him.
We lost the other one at 8 plus. So we know by the time we are getting to 9, the 8 plus person has also disappeared.
Yes.
Is that okay?
Yes.
So that's why 4 minus 1, then minus that other one that was lost, then we are left with the 2. Then how many people die in time point 9? How many people die within time point 9?
1.
1. So what is the probability of surviving time point 9? 1 over 2. Is that okay? Guys, remember, these are survival at those time points only. At those time points only. Is that okay? Now, the survival function now itself, ST. How many people survive up to time point 1? It will be exactly the 7 over 8. Is that okay? Is that okay? Hello? Then now, to survive up to time point 2, it means you survive time 1 and you survive time 2. So it means because they're independent events, we need to multiply the 2 probabilities of survival. Is that okay? So to survive time point 2, it means you've survived time 1 and you survived time 2. So you need to multiply the survival of time 1 and survival of time 2 to get this value here. Is that okay? So it will be 7 over 8 times 4 over 6. What do we get? So we take this, multiply by that. What do we get? 7 over 12. Is that okay? Then to get this survival here, then it means you survive time point 1 and time point 2 and time point 3. So we multiply this survival and the next survival time, which is this one. What do we get? Is it 7 over 16? Yes, 7 over 16. Is that okay? Then the next one, we multiply this and that. Gives us what? 7 over 32. Guys, remember, to get the survival, remember, these are the probabilities of survival. Is that okay? But to get survival up to a certain time point, you must multiply. Remember, this is the symbol of product. This big pi is the product. So you have to multiply all the probabilities up to the current point of interest. Is that okay? Is
I
that
have
okay?
a question.
Please shoot.
Is it not the same as saying the probability of A given B?
It is the same.
Will the formula still remain the same?
Which formula?
The intersection of A and B over B. The probabilities of the intersection of A and B divided by the probability of B.
So you're asking if it is the same as what?
Our calculation, that is.
Mm-hmm. We are saying that for 2, yes, you can also look at it from that way. The intersection here, yes.
Ideally, the intersection is the product of the
product. That's what I'm saying. Yes, 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 yes.
Then
so
we divide further.
No, you don't divide. Because you just make this the subject of the formula. You multiply with this. So it will be the probability of A given B times probability of B.
Okay.
And if I want to make it easy for you, 2 events are independent, A and B. What is the probability of A given B?
I think it's the first probability before we reach the second probability.
No. If A and B are independent, what is the probability of A occurring given B has occurred? Probability of A. It will just be equal to probability of A.
Yeah, probability of A.
Then now, if you are looking for the intersection from the right-hand side, you can take it from this side. The intersection will just be the product of the 2 probabilities. Let me make it simple with an example. Is that okay? If you have, let's say, if you have 10 ladies in a class and 5 men in a class, is that okay? If you have 10 ladies and 5 gentlemen in a class, is that okay? If you pick somebody randomly, what is the probability that it's a lady? What is the probability of picking a lady in that class?
It will be the total number of ladies over the total number of students.
I've given you the numbers already. If you have 10 ladies, 5 gentlemen, what is we need in terms of numbers? We are teaching. We are teaching.
10 over 15.
We are teaching. So when teaching, you have to use exact the same numbers that you used in your when you are describing your problem, so that students are able to link your answers with what the problem was. If you have 10 ladies and 5 men, what is the probability? If you pick somebody randomly in that class, what is the probability that it's a lady?
Ten over 15.
It will be 10 over 15. Is that okay? Now, what is the probability of picking a lady given that we've removed a chair from that class? Or we've removed a blackboard from that class. What is the probability of picking a lady? I ask again. What is the probability that a person that is randomly chosen is a lady, given that we've removed a whiteboard from that class? What? Hello?
10 over 15.
Why 10 over 15? Because removing the whiteboard and picking a lady are 2 independent events. One does not affect the other. If you remove the whiteboard from the classroom, it will not change the number of students or the number of ladies in the class so that the probability changes. So those 2 events are independent. So the probability of picking a lady because the two events are independent. Is that okay? That's why here probability of A given B will just be equal to probability of A, because A and B we've already said they're independent. But anyway, I think let us not go that direction so much. Let us be here. Are we okay with the calculation of this survival function?
Yes, we are.
Any question on this? Is anybody able to share his or her R screen so that we try and calculate the same? Anyone? We need somebody to also save these values. We'll be reading these values in R. So it's a small data, so we'll read it very quickly. Is that okay? We need another person to convert these fractions for us. These fractions at the end here, in decimal form, so that we're able to compare with what R will be giving us. Just dividing this fraction and keeping the answer somewhere. Anyone who can share the screen quickly, guys, I'll guide you on what to do. Hello? Hello? Maybe you can just share screen. If you share, Abigail. Yes, I hear you are not able to speak, but are you able to just show the screen, then we tell you what to do without you speaking? Yes, then share the screen, we tell you what to do, because the others are not able to share. Guys, the best option that we have is Abigail to share the screen, but her mic has a problem, so she'll not be able to speak. We'll be able to tell her what to do, but she cannot talk back to us. The other option is somebody else volunteers to share his or her screen. I think we don't have any other option. Abigail, are you able to share a screen now? We go with you. So members will read these values, so keep them somewhere so that we read them, the values on the screen. So let me stop sharing. So I'll share the hand calculation for Kaplan-Meier once we are done with the class. So Abigail is sharing her screen. Okay. So the same data that we did by hand, we want to do it using R. Is that okay? So to enter this data, we need to enter it in using two vectors. One vector to show the actual time values, the ones that we are given. Then the other vector is to show which one was a failure time and which one was a censoring. Is that okay? Guys, I'm talking to you. Remember, Abigail is only listening and typing, nothing else. Hello? I'm saying for us to be able to enter the data that we had, we need to enter it in two vectors. One vector to give us the actual values that are recorded, and the other vector to tell us which ones are fully observed failure times, we record using 1, and the sensor times we record using 0. Is that okay? So we need to enter the first. So we enter those ones as time. So create a vector called time. Abigail, type time is equal to C for vector. Then we read in the values. The first value is 1, 5. So we put all the values irrespective of whether they are censored or not. Then we'll define another vector which tells us which one is a failure time and which one is a censored time. Is that okay? Then we read another vector called status. We could have given them any other names, is equal to C. So we give it a 1 if it is an observed wabiro malokani. We give it a 1 if it's a failure time, and we give it a 0 if it is censored. Yeah. So that's correct. Is that okay?
Yes.
Then now we need to create a survival object from these two. We need to create a survival object. To create a, so put a comment. Oh, sorry. Put a comment then. To do survival analysis, we need a package called survival, everything lowercase. To do survival, we need a package called survival. So to load the package, we use the function library, then into bracket survival. No, it's already installed. It comes with R automatically. So we only need to load the package using library. So survival usually comes by default. So we only need to load it using library function. Have you run it already? Okay. So proceed, next line. We need to create a survival object. We need to create a survival object using the serve function. Create a survival object using the serve function. The serve, this is one of the few functions which start with capital letter. So serve, then you start with the time, then comma status. Save that survival object. Give it a name, the survival object. Give it a name, whatever name you want to give it. Any name. Okay, Beles, okay. Run it. Then now view Beles. You now see that it has created the survival object. So you just run the Beles. You can just run the Beles. It's okay. No, run the Beles. Just run Beles only. And you see it has now created the same objects, but with the you see it has created, it has fused them and shows where the censoring are. So always when you do this, make sure you check first to see the censoring are placed at the right places. Is that okay? Okay. Then now we've created the survival object. The next thing is to do Kaplan-Meier estimation now. Is that okay? To do this, we use the function called survfit. Survfit Kaplan-Meier estimation.
Is it that one?
And I say the function is called, the problem is that you need to write the name of the functions in your comments so that somebody knows. So the function itself is called subfit, one word, subfit. And I was just explaining that it is used to estimate the Kaplan-Meier, to get the Kaplan-Meier estimator.
Is it this one?
Just read your comment. Read your comment first. Is that what is your number 12 related to your comment?
There is no KM.
So subfit, then you start with the object name, the object that we created, the survival object. Then tilde, the ones for regression. Then 1. That's the value 1. We need to give that, we need to give it a name, the estimated value. Give it any name. Okay, call it KM, it's okay. Run. Is that okay? Do names into bracket KM to see what else is stored under KM. Names into bracket KM. So which object do you think could be storing the survival values? These are objects created. Which one do you think is storing the survival values? Serve. Yeah? Correct? How do you access that serve value, the serve values? We did this in regression. Yes, we use $sign. Run. Somebody, I told you to convert the survivals that we estimated, the survival values, I told you to convert them to decimal. Did anybody convert? Are they the same values? Mm-hmm. Mm-hmm. Remember, it's showing for all the 8 values, but remember, we only need to focus at the other values, the failure time values. So we don't repeat we don't put the sensor. For sensors, it remains 0.87 again. Is that okay? So the second value, the uncensored one, is 0. The next value uncensored is? The next value uncensored is? So it's exactly the same. So it's what we had in our table, which we did by hand. But if you divide the values, the fractions, you get these values. Is that okay? The other important thing to show is the Kaplan-Meier survival plot. The Kaplan-Meier survival plot, which is important to show, which is the survival function plotted. And we say that it's a decreasing function, starting from 1 going down towards 0. Is that okay? So to do this, we use the function plot, then into bracket the KM object. Plot then the Kaplan-Meier object. So I'm not talking about the survival object, I'm talking about the Kaplan-Meier object. So you do plot into bracket, then the object that created the survival function, where we store the survival values, not the survival object, the estimated survival function.
I am.
Where we stored the estimated survival values or function. It's KM, yes. Run that one. So that is the survival function. The survival function, when you do it, is usually a step function. At step function, it goes down in a step format. Is that okay? So this is the survival function. It's a decreasing function starting from 1 going downwards. Is that okay? Guys, in summary, what we've done today, we've introduced survival, we've discussed censoring, we've discussed causes of censoring, we've discussed the four most important functions, but we've only focused on 3. We've discussed the 4 important functions in survival analysis. The first one is the ST, which is the survival function. We have the lowercase ht, which is the hazard function or instantaneous failure rate. Then the third function is the ft, which is the density function. And the last function is the capital HT, which is the cumulative hazard function. Is that okay? Then we discussed several ways of estimating the survival function. We say that there are 3 approaches: the parametric, semi-parametric, and non-parametric. The non-parametric, we say that the particular method for estimating survival function that is non-parametric is called the Kaplan-Meier estimator, or the product limit estimator. And by non-parametric, we say that we just calculate it using the data itself. We don't assume any distribution or parameters. Is that okay? Then we've gone ahead to compute the survival function by hand, of which we've seen the value, and you should be able to produce this similar plot by hand, given data. Then we've seen how we are able to use R to fit in the survival function and produce the survival plot. We've seen that the first step is to read in the survival data, and we need to read it using 2 vectors, one that stores the time values and another one that tells us whether it is a failure or a sensor, where failure is given a 1, a censoring is given a 0. Is that okay? Then once you read in the data, the first thing you need to create is a survival object, which you create it using a function called surv, S-U-R-V. The S is capital letter. These are some of the few functions that start with capital letters in R. Most of the functions in R start with the lowercase letter. But survival function, especially this one of creating survival object and handling complex numbers in R, also uses capital letters. So to create a survival object which combines the 2, the survival and the status, or failure status, we use the sub function. Then to fit the Kaplan-Meier estimator, to get the Kaplan-Meier estimator of the survival function, we use a function called subfit or subfit in R. Is that okay? Then once we estimate the Kaplan-Meier, we can get once we get the values, we can plot using the plot function. You just give the object from subfit into the plot function, and it will be able to know that you want to produce a Kaplan-Meier plot. So this plot is what we call a Kaplan-Meier plot. Is that okay? What we'll do next, not today, in the next class, so we'll have to do one more class next week, is comparing survival functions for 2 groups. For example, let's say we have female and male, and we want to check whether the males are dying more, are surviving more compared to the females, then we need to compare the survival function for males and females. Is that okay? To do that, we use something we call the log rank test. Log rank test. log rank test to compare the survival function. Is that okay? And so we'll do some theory about it quickly. Then we will do some R codes to do the log rank test for comparing two survival functions. Is that okay? Which one is higher than the other? Then after that, we'll discuss now the regression framework. Now, if you want to check whether there are some factors that are influencing the survival function, we do that, but we don't use the survival function itself. We use the hazard function and throw a semi-parametric model called Cox proportional hazard model, or the Cox pH model. So the Cox pH model, through it, we can estimate the survival function, but we can also check the effect of covariates. So if you want to know whether some covariates are increasing survival or decreasing the survival rate, then we use Cox pH model. Is that okay? For example, we might have now two sets of data set. One data set of survival for those who received a drug, and one data set of survival for those who received placebo or did not receive the drug. Then we can include those ones in a regression framework using the Cox pH model and be able to know, does the drug that was used, does it help in increasing survival? Is that okay? So we'll do all those in the next class. So in the next class, we'll do two things, log rank test and Cox pH model. And we'll stop there. So you can read ahead in the remaining one chapter where we are covering log rank test and the Cox pH model. Unless there is any burning question, I hope to stop there. Any question? So our last class will be next week. That will be our last class for this unit. I was hoping to finish today, but the content seemed like more than what I could chew today. Any burning question? If there is none, allow me to stop there. Again, thank you for your time. I'll share with Abigail the screenshots for today's derivations so that she's able to share with you. For the R codes, you can get from her. So Abigail, you can share the R codes for estimating Kaplan-Meier and also plotting the Kaplan-Meier. Is that okay? Thank you, guys. Sorry for the delay today. I think I took more time than I was anticipating, and yet I didn't finish. So we do our last lecture next week. Thank you, guys. Enjoy the rest of your evening.
You too.
Okay, bye. Please read that book. You know, I was covering